Standard and factored graphs. In this video, you'll learn the meaning of the intercepts on a graph of a quadratic function in terms of the situation it represents. You'll also learn how the numbers in the factored form of a quadratic expression relate to the intercepts of its graph. So the standard form of a quadratic expression is written as a sum of ax²+bx+c. And the factored form of a quadratic expression is written as a product of two linear factors, as x plus m times x plus n. The intercepts of a graph are where it crosses the x and y axis. So let's look at some examples. The function h of t equals negative 16t squared plus 78t plus 10 can model the height of an object thrown from 10 feet with a vertical velocity of 78 feet per second. So let's take the function they gave us and analyze its pieces. We can see that a is negative 16, b is 78, and c is 10. Jada said that the equation g of t equals negative 16t minus 2 times t minus 5 also defines the function but in factored form. Is she correct? So let's take the function that she gave us and we'll expand it to see if it simplifies to what we have for h of t. So we'll distribute the negative 16t minus 2 to t minus 5. So we'll start with negative 16t times t minus 5 minus 2 times t minus 5. Multiplying negative 16t times t will give us negative 16t squared. And distributing negative 16t to negative 5 will give us positive 80t. Now we'll distribute the negative 2, so we'll multiply negative 2 by t, which gives us negative 2t. And now we'll distribute the negative 2 to negative 5, which gives us positive 10. We'll combine our like terms of positive 80t and negative 2t, and this gives us a final equation of negative 16t squared plus 78t plus 10. And now we can see that it matches our function of h of t, so Jada is correct. This graph represents the original and Jada's function. What are the intercepts and what do they mean in this situation? If we look at the graph, we can see that the x-axis represents the seconds and the y-axis represents the feet. We can see that our y-intercept happens here at the point 0, 10. So this tells us that the initial height of the ball was 10 feet, since 0 seconds have passed. If we look at the x-intercept, this happens at the point 5, 0. So this tells us the ball hit the ground after 5 seconds, since the height would be 0. In this example, we're going to identify the x and y intercepts for each function. Our first example in standard form is x² plus 4x plus 3, and in factored form, it's x plus 3 times x plus 1. So if we look at the graph, we can see that our y-intercept happens at 0, 3, and our x-intercepts happen at negative 3 and negative 1. In our next example, x squared minus 5x plus 4 is in standard form, and in factored form, it's x minus 4 times x minus 1. We can see the y-intercept happens at 0, 4, and the x-intercepts happen at 1 and 4. So let's summarize the x and y-intercepts for each pair of functions that we were given. If we look at the y-intercepts, we can see that they come from the standard form from our constant term. And if we look at our x-intercepts, they come from factored form when we solve each parenthesis for 0. So we'll keep this in mind as we look at a couple more examples. Without looking at the graph of the function, what are the x-intercepts of f of x equals x minus 7 times x plus 3? So we'll take the function they gave us, and we know that we want the value of this function to be 0 so that we can find the x-intercepts. So we'll set each parenthesis equal to 0 and then solve for x to find those intercepts. We'll start by adding 7 on our first equation to get x by itself. This gives us a value of x equals 7. Now we'll solve the other equation by subtracting 3 from each side. And this gives us a value of x equals negative 3. So our x-intercepts happen at 7 and negative 3. Now we're going to use the distributive property to convert this to standard form. So we'll take our first parenthesis and distribute it to the second one. This gives us x times x plus 3 minus 7 times x plus 3. So if we distribute the x, we'll get x squared plus 3x, and if we distribute that negative 7, we'll get negative 7x minus 21. Now we can combine our like terms of positive 3x and negative 7x So our equation in standard form would be x squared minus 4x minus 21. What are the x-intercepts of the graph of the function defined by x minus 2 times 2x plus 1? We'll start by setting each parenthesis equal to 0, since the value of the function would be 0 if we're looking at the x-intercepts. We'll start by adding 2 to both sides on this equation, and we get x is equal to 2. In the next equation, we'll start by subtracting 1 from each side, and this gives us 2x is equal to negative 1. Now we'll divide both sides by 2, and get a final answer of x is equal to 1/2. So the x-intercepts would happen at 2 and 1/2. In our last example, we're going to use this graph to write an equation in factored form given its x-intercepts. We can see that it crosses the x-axis when x is negative 1 and when x is positive 3. So we can represent x equals negative 1 by x plus 1 in parentheses, since solving for it will give us a negative 1 that we have. And x equals 3 can be represented by the parenthesis x minus 3, since solving for this will give us the positive 3 that we want. Let's summarize what we've learned. Different forms of quadratic functions can tell us information about the function's graph. When a quadratic function is expressed in standard form, it can tell us the y-intercept of the graph that represents the function. And when a function is expressed in factored form, it can help us see the x-intercepts of its graph.